Hello, this is Ashwin. In this video, I'll be solving paper 4 variant 2 February-March 2019 0625 physics. Starting with question number 1a, define acceleration. So I'll just write the formula over here. So acceleration is change in velocity divided by the time taken for the change. B, figure 1.1 shows the distance time graph for the journey of a cyclist. 1. Describe the motion for the cyclist in the time between 0 seconds and 5 seconds. Alright, so between 0 and 5 seconds, the cyclist is accelerating since this is an upward curve. Between time 15 and 30 seconds. Alright, so up to 15 to 30 seconds, this is a constant speed graph represented by a straight line. Between time 30 and 40 seconds. Alright, so over here the cyclist is decelerating. To calculate for the 40-second journey the average speed. So the average speed is the total distance covered, which is 300 meters divided by the time taken, which is 40. So we have 300 divided by 40, and that gives the speed as 7.5 meters per second. To the maximum speed. So this up to 15 seconds, the cyclist is accelerating, which means each second his speed is increasing. So it is not going to be over here since each second is less than the next second. So 15 is the point where he stops accelerating, which means the highest speed is over here, and then he continues for the same speed up till 30 seconds. So the difference between these 2 points, the change of distance, and that is to say the change of speed over the period of 15 to 30 seconds, is going to be giving the highest speed or the maximum speed, and that is going to be equal to the change of distance, which is 250 minus 70 divided by the change of time taken, which is 30 minus 15, and that is equal to 12 meters per second. Question number 2a, state one advantage and one disadvantage of using a wind turbine as a source of electrical energy. Alright, so the advantage is that it creates no pollution by emissions of any sort of gas, but due to these large blades over here, it can cause death of birds. B, figure 2.1 shows a wind turbine. 1. The wind blows at a speed of 16 meters per second towards the turbine blades. In 1 second, a volume of 24,000 meters cube of air passes through the circular area swept out by the blades. The density of the air is 1.3 kilograms per meter cube. Calculate 1. The mass of the air that passes through the circular area swept out by the blades in 1 second. Alright, so we have volume and density given over here. So mass is going to be equal to density multiplied by volume, which is equal to 1.3 into 24,000. So mass over here is going to be equal to 31,000 kgs. To the kinetic energy of the mass of the air that passes through the area swept out by the blades. Right. So we have the formula of kinetic energy as half multiplied by mass into velocity square, and that is equal to half into mass, which is 31,000, multiplied by velocity, which is 16 given in the question, squared, and this gives the answer as 4 into 10 to the power of 6 joules. To suggest why some of the kinetic energy of the air that passes through the circular area swept out by the blades is not converted into electrical energy. That is because some of the energy is required to oppose the friction which is caused by the blades over here, so that is not converted into electrical energy. Question number 3. An object is moving in a straight line at constant speed. State three ways in which a force may change the motion of the object. Along with its speed, but there's only one other mark left. So I'll just say increase and decrease its speed. B. Figure 3.1 shows an object suspended from two ropes. The weight of the object is 360 Newton. The magnitude of the tension in each rope is T. In the space below, determine the tension T by drawing a vector diagram of the forces acting on the object. State the scale you'd use. Alright, so this question is a bit different from its usual form because the forces or two of the forces would be given along with an included angle, but this can also be solved by a similar method. So the object is stationary, which means there should be no resultant force. The total forces upwards should be equal to the total force downward. And suppose there's a vertical force of T over here and another of T over here, and they should be equal because these two ropes have equal forces and that equal tensions, and that should mean a vertical force over here would be equal to a vertical force over here. So the forces would be acting upwards to lift the weight of the object, and the sum of total upward forces should be equal to 360, which is let's label this force over here x and x. They're going to be equal. So 2x should be equal to 360. And so x is going to be equal to 180. Alright, so here, let's say we have the magnitude of this force as 180. Now we want to know the size of t. So we have an angle, its opposite side, and the hypotenuse side is required. So sine 45 is equal to opposite, which is 180 divided by the hypotenuse side, which is t. So t is going to be equal to 180 divided by sine 45. And so t is equal to 254. So I'll round it to two significant figures, and so it becomes 250 newtons. Alright, so now we have calculated the size of t, which means we can now draw the parallelogram. And first we need to decide the scale. I'll write the scale over here. The scale I'll be using is 1 centimeter is equal to 50 newtons. And that should mean 250 newtons divided by 50. So my T over here is going to be equal to 5.1 centimeters. This is the center of my scale. Alright, so here is my center of the scale. I'll draw a line which is 45 degrees from the center, and it's supposed to be 5.1 centimeters long. But I'm not going to be drawing the diagram to scale since the space over here is not sufficient. Alright, so let's suppose this line over here is 5.1 centimeters. I'll label it. Similarly, The other side is also going to be equal to 5.1 centimeters, drawn at an angle of 45 degrees. I have 45 degrees over here. 5.1 centimeters, both of the lines. And you need to have opposite sides of this parallelograms equal in figure. So I'll draw a line over here. Similarly, an equal line over here, which is supposed to be equal to its opposite line, or the line which is parallel to this one. So the line here and here are these lines are supposed to be parallel, and similarly these two lines are supposed to be parallel. And once you measure this line, this should be equal to 360 newtons. And of course, this is not going to be 360 centimeters or anything. My drawing over here should be equal to 7.2 centimeters, so that when I multiply it by 50 and convert it to newtons, this should be equal to 360 newtons. So the T over here, as we got in the calculation, was 250 newtons. And that is how you draw this vector diagram. Question number 4a. Figure 4.1 shows a mercury barometer. The tube containing the mercury is vertical. 1. The height h indicates a value of atmospheric pressure. State what is contained in the space S. So over here, this space is vacuum, so that there is no air present in here, and that is required to have no pressure. If there was pressure over here, we wouldn't be able to calculate the atmospheric pressure coming from the upper surface of the mercury. So we do not need any pressure over here. In fact, we don't want it. So that is why we have vacuum over here. 2. On a particular day, the atmospheric pressure is 1.02 into 10 to the power of 5 pascals. The density of mercury is 13,600 kilograms per meter cube. Calculate the value of height indicated by the barometer. Alright, so pressure is density into gravity into height, and so height is going to be equal to pressure, which is 1.02 into 10 to the power of 5 divided by the density multiplied by gravity. So that is going to be equal to 13,600 into 10, and this is equal to 0.75 meters of height. 3. The tube containing mercury is now tilted so that it makes an angle of 10 degrees with the vertical. After tilting, there continues to be a space above the mercury in the tube. State and explain whether the vertical height of mercury in the tube is smaller, the same, or greater than the value calculated in A part 2. Right, since over here we need to know if any change occurs in height. We need to see if any changes is occurring in any of these values, and that is not occurring, which means pressure, density, and gravity remains the same, so height also does not change. B. Another mercury barometer in the same room at the same time shows a lower value of H than the barometer in A. Suggest and explain a reason for the lower value. Alright, so suppose if here there was some amount of gas, that is to say, this space S was not vacuum. There was air over here, so that would have applied pressure on the mercury over here, and that could have been the reason that the height reduced, since pressure over here is also applied, and so it is applied over here due to presence of air, and that would mean reduction in height. So that is going to be the answer. Question number 5. A. State the values of the fixed points of a temperature scale, that is the melting point and the boiling point, which are 0 degrees Celsius and 100 degrees Celsius. B1. The graduations on a liquid and glass thermometer are equally spaced. For the equal spacing of the graduations to be correct, state 1. An assumption that is made about the liquid in the thermometer. Alright, so the assumption is going to be that the liquid expands uniformly, which means for each degree change of temperature, the liquid expands the equal length. 2. An assumption that is made about the structure of the thermometer. Capillary tube has constant width throughout the length. 2. Liquid in glass thermometer A has greater range than liquid in glass thermometer B. State one way the design of thermometer A is different from thermometer B. So this could be longer than B. Three, liquid in glass thermometer C has a greater sensitivity than liquid in glass thermometer D. State one way the design of thermometer C is different from thermometer D. Alright, so the liquid in C has greater expansion rate. C1. In the space provided, draw a label diagram of a thermocouple thermometer. Alright, so in a thermocouple thermometer, first have a voltmeter connected to two wires of different metals. So these two over here are going to be copper wires, and this one over here is iron wire. And one of these junctions is going to be hot and the other junction is going to be cold. To suggest when a thermocouple thermometer is more suitable than a liquid in glass thermometer. Then we have a higher range because this is quite suitable for high ranges of temperature. Question number 6. An electrical heater is placed on the floor of a room in a house. The heater is switched on. A. State the main process by which thermal energy is transferred to air in all parts of the room. So thermal energy is transferred by convection currents, because thermal transfer of thermal heat through air is carried out by convection, which basically transfers heat through liquids and gases or fluids. B. The heater has a power of 1.5 kilowatts. The air in the room has a mass of 65 kilograms. The specific heat capacity of air is 720 joules per kg degrees Celsius. 1. Calculate the time it takes for this heater to raise the temperature of the air in the room from 8 degrees Celsius to 15 degrees Celsius. Alright, so specific heat capacity is equal to energy divided by mass into change in temperature. But over here, energy directly is not given. Instead, we have it in the form of power into time, and time here is unknown. Rest of the values are given. So first I'll start by calculating the change in temperature, which is 15 minus 8 degrees, and that is equal to 7 degrees Celsius delta temperature. And then I'll substitute the rest of the values, which is equal to, so the time here is going to be equal to specific heat capacity into mass into change in temperature divided by the power. Alright, so we have 720 into 65 into 7 and the whole fraction divided by 1500. And so the time is going to be equal to 218 seconds corrected to two significant figures is going to be 220 seconds. To state two reasons why time calculated in B1 is smaller than the actual time taken to raise the temperature of air in the room from 8 degrees Celsius to 15 degrees Celsius. That's because that is the only calculated time to heat the air. But in reality, the heat may be lost by windows or absorbed by the furniture. I'm going to be writing heat. 7a. In figure 7.1, the small circles represent molecules. The arrows refer to the change of state from arrangement of molecules on left of the arrangement of molecules on the right. Complete the following by writing solid, liquid or gas in each of the blank spaces. So change of state X is from solid to liquid. Change of state Y is from liquid to gas. B. Explain in terms of forces between their molecules why gases expand more than solids when they undergo the same rise in temperature. So weaker forces is the reason between gases. Forgot to write due to weaker forces of attraction between gas molecules. C. A cylinder of volume 0.012 meters cube contains a compressed gas at a pressure of 1.8 into 10 to the power of 6 pascals. Right, a valve is opened and all of the compressed gas escapes from the cylinder into the atmosphere. The temperature of the gas does not change. Calculate the volume that the escaped gas occupies at the atmospheric pressure of 1 into 10 to the power of 5 pascals. So first off, we need to calculate the volume of the gas which was compressed when it is not being compressed. That is the volume of gas at normal pressure. So P1 V1 is equal to P2 V2 P1 was 1.8 into 10 to the power of 6 multiplied by V1, which is 0.012, and V2 is going to be equal to P1 V1 divided by P2, which is 1 into 10 to the power of 5 pascals. So V2 is going to be 0.216 meters cube. But this is the volume of the gas, the total gas, and some of it remains in the cylinder. Now we need to calculate the volume which has escaped. So that is going to be the volume of total. I'll round it to two significant figures over here. So that is going to be 0.22. This is the volume of the total gas minus the gas which remains in the cylinder, and that is going to be the volume of the cylinder itself, and that is equal to 0.208 rounded to 0.21 meters cube. This is the gas which escapes out of the cylinder. So initially this volume of gas was compressed into 0.012 meters cube, and the pressure was higher than atmospheric pressure. Once the valve was opened, some of the gas escaped, and the only remaining was 0.012, which is the volume of the container, since pressure applied is not going to be higher than atmospheric pressure. 8. Figure 8.1 shows parallel wavefronts of a light wave in ice. The wavefronts are incident on a boundary with air, right? So it's traveling from ice to air, which means it is traveling from denser medium to rarer medium, and so the reflected rays would be moved away from the normal. So the speed of light wave in air is 3 into 10 to the power of 8 meters per second. The refractive index of ice is 1.3. A. On figure 8.1, draw the wavefronts of the wave that passes into the air. 2. Draw arrows to show the direction of travel of the refractive ray. 3. Label the angle of incidence I and the angle of refraction R. Right, so I'll start by drawing the wavefronts of the wave that pass into the air. Alright, so I'll first start by drawing the normal over here, which is perpendicular to the boundary. Alright, so here I have my normals, and this is going to be this is supposed to make the refraction easier for me. So here we have the angle of incidence. I'll just label it right now, incidence, and the reflected rays are supposed to be moving away from the normal, since this is traveling from denser to rarer medium. And the refracted rays should be parallel to each other, just like the incident waves are. Alright, that's it, and this is angle of refraction. Now we need to label the direction of wave motion, which is this way, which is perpendicular to the wavefront. B. Calculate the speed of light in ice. Alright. So refractive index is equal to speed of light in air divided by speed of light in substance. So that is going to be equal to B is speed of light in air divided by refractive index, which is 3 into 10 to the power of 8 divided by 1.3, and that is right. So this is 2.3 into 10 to the power of 8 meters per second. Question number 9. Figure 9.1 shows a current potential difference graphs for a Figure 9.1 shows current potential difference graphs for a resistor and for a thermistor. Calculate the resistance of the thermistor when potential difference across it is 7 volts. Alright, so here we have the graph of the thermistor and the potential difference is given as 7 volts. And so we can trace it back to the y-axis of the graph, and this is equal to 4.6 amperes. And so resistance is voltage divided by current. Voltage given in the question is 7 divided by current. When you gain it from the graph is 4.6. And so the resistance is going to be equal to 1.5 ohm. In table 9.1, tick the boxes that indicate the effect of the resistance of the resistor and of the thermistor when potential difference across them is increased from 0 to 7 volts. Alright. As you can see over here, the graph of resistor is constant, which means the gradient is constant. This is a straight line, which means the gradient is constant, and so the resistance does not it neither increases nor decreases, and it is the same. It is constant. Alright, so for thermistor, the resistance over here decreases. You can make this out by the graph given over here. If you calculate resistance at two different points, you would see that as you go forward, the value of resistance would be decreasing. And so over here, I've marked the decreases box. See, the thermistor and the resistor are connected in parallel to a 7 watt supply. And that means both of them get 7 watts of potential difference across them. Calculate the current from the supply. Alright. As we can see over here in the graph, at 7 volt of potential difference across them, they have the same current, and that means 4.6 over here in the graph. So 4.6 plus 4.6 of each is going to be equal to 9.2 amperes. 4.6 plus 4.6 is 9.2 amperes. Since they are connected in parallel, the current between the resistor and thermistor is divided, so we'll add them to calculate the total current supplied by the source over here to the energy transferred from the supply in 5 minutes. So energy is equal to power into time, and power itself is going to be voltage into current multiplied by the time from the previous equation. Voltage is 7 multiplied by current of source multiplied by time. I'll convert 5 into seconds by multiplying it by 60, and that is equal to 19,000 joules. Question number 10a. The electrical energy produced by a power station is transmitted over long distances at a very high voltage. Explain why a very high voltage is used. Right, so increasing the voltage decreases the current, and so the heat loss by current decreases. And since the heat loss decreases, we can use thinner cables because they don't need to have tolerance for high heat, and also reducing the thermal energy lost reduces the cost. B figure 10.1 represents a transformer. The primary coil P has 4000 turns and an input of 120 volts, 120 voltage. The secondary coil S has an output of 9 volt. Calculate the number of turns in the secondary coil. So here I'll be using the formula. Primary voltage divided by secondary voltage is equal to number of turns of primary coil divided by number of turns on secondary coil, which means number of turns on secondary coil is going to be equal to number of turns on primary coils, which is 4000, multiplied by the secondary voltage, that is 9, divided by primary voltage, which is 120. And so the number of coils on secondary coil is going to be equal to 300. To state a suitable material for the core of the transformer, this can be iron, which because we need a material which can be easily magnetized and demagnetized. 11A1, one isotope of iridium 194 is represented by the symbol over here. This isotope decays by beta emission to a stable isotope of platinum. Complete the nuclide equation for this decay. Alright, so beta decay means no change in the mass number, so it remains the same. However, the atomic number increases by 1 because over here we have -1. So this one over here is 78 and this is 194. 2. The half-life of iridium is iridium 194 is 19 hours. A sample of iridium 194 has an initial count rate of 1100 counts per minute. Calculate the count rate from this sample after 38 hours. So first we need to see how many half-lives have passed in 38 hours, which is going to be equal to 38 divided by 9, and that is 2 half-lives, which means this amount 1100 counts per second is going to be reduced by half twice, and that is 1100 divided by 2 is equal to 550. So one half-life has passed. The second one again reduces it by 2, which leaves with 275 counts. So that is the answer per minute. State 2 is in which gamma emission differs from beta emission. Right. So first off, this is a part of electromagnetic radiation. And beta emission is not a part of electromagnetic radiation, and however beta emission is just an electron. Alright, so we are done with this paper. Thank you for watching.